Okay, so next in a series of complex kinematics problems, let's see. Several children are playing delay tag, where the person who is it must stay still counting to 10 before they can chase anyone who is not it. All students start from the front door of the school when they run, including the student who is it. Student A is chosen to be it and can run at 6 meters per second. The other students begin running away from student A while the student counts to 10. After waiting 10 seconds, student A chases student B, a specific student, who runs at 4.2 meters per second. So what we've got here is we've got the school door. We've got a couple of students. Let's go with student A. Student A can run with a speed of, so VA, is equal to 6 meters per second. Student B, whom student A will chase, can run at 4.2 meters per second. Now that would honestly be very bad for student B, probably still is, except student B gets a head start because student A has to count to 10 before they can start running. Now, you can assume that the students, whenever they start moving, they start going immediately at their top speed. It doesn't take people very long to get up to their full speed. And so we're not like a train that has to slowly increase speed. We can usually get up to full speed very, very quickly. So we're going to approximate this by saying that when they start running, they just run at that constant rate. Okay. So my question is this, and much like one of the previous ones we looked at, I've got several things that we're going to have to solve, and we're going to have to solve them together at the same time. This is another example of simultaneous equations. Words are hard. Okay. Here's what we got. We got two objects that we're going to track the motion of. So I'm going to do delta XA, v final A, v initial A, acceleration of A, and time of A. We're going to look at the motion of student A, who's going to do some stuff and chase down student B. Delta XB, how far student B goes. The final velocity, or speed, of student B. The initial velocity, in this case, velocity and speed will be the same because they're both just going to be going to the right, the way that I've drawn this. And we've got our acceleration of B, and we've got the time for the motion of B. Okay, great. The acceleration of student B is 0 meters per second squared, and the initial and final velocities are going to be 4.2 meters per second. Student A is 6 meters per second, and the acceleration is once again 0 meters per second squared. Beyond that, we don't know too much. We do know that student B is going to do some running. And get some distance away, maybe over here. But while student B is running, eventually student A starts running afterwards, and because student A is faster, student A will catch up eventually with student B at some location over here. Now that's one of the things that I ask for, but I also ask how long it will take student A to catch student B. Now I will say this, student A will eventually start moving and go chasing after student B and eventually make it here where they catch student B. Now, like one of the others that we talked about, we need to set up relationships because we know neither the times nor the displacements. In this case, student A and B both start at the door, but student B gets a head start running. So they start here in their motion, whatever that motion is, and they end over here where student A catches student B. What that means is both of their displacements will actually be the same. In this case, I'm just going to replace, instead of having delta XA and delta XB, I'm just going to call it delta X. It's going to be the total displacement for both of them. So if we find it for student A, we know what it is for B and vice versa. The hard part's going to be back down here. We need a relationship between their times. They don't run for the same amount of time. Student B gets a head start. So they would start and they get to run for 10 seconds longer than student A. And this is one of those places where you have to stop and think about which time is bigger. student B is running for a greater amount of time than student A, so that means we get the following, that time B is equal to time A if time A has an additional 10 seconds. We had 10 seconds, and then student A starts running. Student B is running for that entire time, however long student A is running, plus an extra 10 seconds. Now, it's easy to mess this up and put 10 seconds over here, and you will get a different outcome. And that's why it's important to stop and ask yourself, what's going on here? This is the really hard part to set up. But we've got ourselves some simultaneous equations. So here is a relationship between our times, and we know that both of their displacements are the same. But we still have three unknowns. We've got time B, time A, which is some of the stuff we're looking for, and how far they end up going, delta x. Okay, great. That's where we use our kinematic equations. So, just like we did in the other video, we know that delta xa, which is just delta x, would be equal to our initial velocity of A times time of A plus 1/2 a t a squared. Okay, delta xa, which we're just calling delta x, it's how far they go, is equal to our initial velocity of student A, that's the person who's actually it. They run at 6 meters per second times however long they're running for, which is time A. Plus, I'm just going to write this in, we have 0, because our acceleration over here is 0, as it many times is, but not always. If it's not 0, put something in there. And you'll end up with another number times ta squared. It'll be a lot harder to solve, but it is still something you can solve. So we get the following. From student A, we know that the displacement of student A, which is the displacement of both of them, is equal to 6 meters per second times ta. We can do something similar with student B, and we'll find that how far they go is going to be equal to 4.2 meters per second times the time of student B. Okay, with this, because both of these are equal to delta x, I can set them equal to each other, like this. And that gives me 6ta is equal to 4.2 tb. But TA and TB are not the same. That's why we still have two unknowns. We need one more equation to sort that out, and that's where we get this. TB is TA plus 10 seconds. So I can do the following. 6TA is equal to 4.2 times TA plus 10 seconds. Plus 10, since I'm leaving the units off the other stuff. I apologize, I'm being a little sloppy, but this video is going to be long enough. Great. This is TB, so I just do a replacement. Like I said, the best way that I've found to work with these is get it equal to some stuff and then put it into something else. Now, you may not know which one to set it equal to and then replace. That's okay. A lot of times you'll have to find both of them, so find whatever you can first and then use it to find whatever the other thing was. Okay, so we'll multiply all this out. I'm going to drop the colors. 6TA is equal to 4.2 TA plus 42. 4.2 times 10. Okay, great. We've got an unknown TA, but it's multiplied by these, so I can do the following. Minus 4.2 TA, but I got to do that to the same thing on both sides. That gets rid of this, and it gets 42 by itself, and we end up with, what is that, 1.8 TA is equal to 42. Great, we're pretty much done. I divide by 1.8, and we get 42 divided by 1.8. We now find that TA, the time that student A is running, is 23.3 seconds. Is that what I was asking, at least when it comes to the time? How long will it take student A to catch student B? Oh, I'm a little open-ended on this. Well, technically, student A is only running for 23.3 seconds, but how long will it take if we include the countdown timer? Student B gets to run for, well, this is TA, and we know TB is TA, this, plus 10 seconds, 33.3 seconds. That is how long student B lasts. Great. That's especially useful because I also asked, how far will they be from the front door of the school when student A or when student B gets caught. Here's a great way that we can actually double check things. We know the following. We said that student A, delta XA, would be equal to 6 times TA, which we now know is equal to 6 times 23.3 seconds. So I'm going to do that 6 times 23.3, and we end up with delta XA, the displacement of student A, is 139.8, probably about 140 meters. Okay, great. We can also find delta XB. Now, if we've done this correctly, delta XB should give me the exact same number. If we don't get the same number, then Sanchez probably made a mistake and he'll have to stop the camera and then reshoot this. But let's find out. 4.2 times TB, well, that would be 4.2 times, we said 33.3 seconds. So 4.2 times 33.3, and we end up with 139.86 meters. Again, in both of these cases, we should probably just round it to 140 meters for our 3 significant figures, but we do get the outcome that we're looking for. This is how we work with it. Again, another complex problem based on the fact that we don't have enough information that is given to us in numbers to just straight up solve it. The hardest part about all of this is by being able to step back and say, okay, what are my relationships? For this problem, delta x's for both of them are the same. This time, our times were different, and how we set that up. This isn't easy. It takes practice. But this is problem solving. If it weren't this, then I could program a computer to solve it. It requires a human brain to approach each of these problems and say, okay, how can I set this up, and how can I get relationships so I can solve for what I'm looking for? That's the true skills that we're trying to develop here. All right.